values of x near 0. Use Taylor series to match the graphs and formulas. Shows the graphs of the four functions below for the values of x near 0. Use the Taylor series to match the graphs and the functions. How are you going to go about doing this? So you don't get stuck doing one forever here. For the first one right here, what does that one look like? Which one can you use, Tina? Yeah, 1 over 1. You could use the binomial series. There's an easier one though. We did this one in class. 1 over 1 minus x squared. 1 over 1 minus y, right? And we let y equal to be x squared. But what does this equal? 1 over 1 minus y. 1 what? Plus y cubed. So therefore, what is this going to be? 1 plus squared plus x to the 6. So there's the quick way to do that one. What about b? What will you have to use for b? Binomial expansion. Binomial expansion. What about the third one here for c? Any ideas? What do you use? What? Give you a hint. Binomial expansion. Correct. That's correct. You can do any direct substitution. You can do any direct substitution you want like that. What is that going to be? You compare it to 1 plus y to the 1/2, and what do you let y equal? X over 2. What about d? What is d? We literally just did the same thing twice, kids. Come on. Everybody stand up. I don't like talking to myself. It's boring. Look at the last one. What can we use on the last one? Binomial again. That's going to be 1 minus y, or 1 plus y if you wanted, to the 1/2. And what do you let y equal? Negative x. Oh, negative, yeah. Done. There you go. So you're using binomial expansion 3 times on this. Using binomial expansion 3 times. So then how can you figure out, once you do these out, is it pretty obvious which one is each? Theoretically, because they're pretty different. So for example, one of them is a parabola facing upwards. So you can work on that. Which one? So which one did you think A was, Cameron? The parabola. Why was it the parabola facing upwards? Exactly. The powers are always going to be even. What it's going to look like is going to be dictated by its highest power, and its highest power is always going to be what? Even. So it's a lot of even powers added together. So what's it going to do? Up. You can do all the other ones like that. Okay, sit down. We're not going to finish this one. We're going to move on to the next one. You can finish this one on your own. It says, what's the question on 20? How do you do that, kids? Negative 1/2. Extension always going to be 1. And then what's the next term? P times whatever the variable is. So it's going to, what's P in this case? So it's negative 1/2 times. Let's keep y for now. Let's keep it as well. We'll do 2 substitutions here. And then what's the next thing? Do you remember? P minus 1, right? So it's going to be negative this times what? Hold on a sec. Times negative 3/2 times negative what? 5/2 over 3 factorial y cubed. How far does it ask us to go on this?
4.
Does it ask us to do 4 terms? 4 terms? Yeah. Okay. That's wonderful. It's kind of ugly. Now, is it just simplifying all of this? Yeah, it's just simplifying. That's it. That's it. What's the first thing you notice structurally when you look at this? What's the new thing you notice structurally? There's a k in it, right? Here's the thing about k. Is k changing? Is k changing? No, it's not. What's the only thing that is changing? What can you do with constants theoretically? You could take them out. So theoretically, you could have e to the negative k times this thing, right? K to the n minus 1 over n minus 1 factorial. Nice. Okay. Terms. Did anybody write out the terms here? Yeah. Does something nice happen when you write out the terms? Yeah, it does. I mean, I looked at this. My original time was like, oh man, we're going to have to know something really, really super creative on this. Like, apply some sort of knowledge of some sum that I don't remember. And man, what happens? So what's the first term? You're plugging in n is equal to what? 0? You put n is equal to 1. Yeah, n equals 0 would be problematic, right? Because you have negative 1 factorial. So you plug in n equals 1. When you plug in n equals 1, what do you get? You get k to the what power? 0 over 0 factorial. Plus, plug in k equals 2, you get k to the first over plus k squared over plus k cubed over what? Does that work? Is that correct? What is this, Cameron? It is e to the x, but it's not e to the x. What is that? That's e to the what? This is e to the what? This is e to the k. This is e to the k. That is e to the k. So what do you now have? E to the negative k times e to the k. What's that? E to the, which is what? 1. It's a cool question. This is e to the k. This is the only difference between this and e to the x is that it's replaced with k. That's it. Are we allowed to do that? Do we care what we call the initial variable? No, we don't care. We sometimes change it so that we can do the substitutions. Makes it a little easier. Okay, please put everything away except a pencil. So what did you prove? You showed that e to the I theta is equal to cosine of theta plus I sine theta. Oh, I'm sorry, I didn't unfreeze it. Sorry. Whoops. Can someone tell me why this is super amazing? Why is this super amazing, Ali?
Because cosine theta gives you all the odd terms.
Yeah, build it. It's kind of crazy that it all fits together so nicely, right?
Because like I has its 6-4 cycle, it doesn't go away for the
evens. Yeah, and then the odds.
But sine theta has all of those terms except without
the I. So you add that in. Exactly, right. Absolutely, right. So what's the cool thing you can plug in for theta to get the nicest truth in all of mathematics? Let theta equal pi, and what do you end up with? E to the pi I is equal to cosine of pi plus I sine of pi. What's cosine of pi?
1.
Not 1. What is it, kids? Negative 1 plus I. What's sine of pi? 0. So what do you end up with? E to the pi I is equal to negative 1. Boom. How awesome is that? That's pretty ridiculous. Think about that. Another way you see it written is you see it as e to the pi I plus 1. What does that equal? 0. Look at that. We have a transcendental, 2 irrational numbers, an imaginary number, 1, and it all adds together to be 0. Isn't that fantastic? I brought this up in assembly. It's kind of cool. You now know how to prove it, which I think is even cooler. But look at that. That right there, if you asked, literally, if you went around the world and you talked to mathematicians and said, write down the 5 coolest things you've ever seen in math, I can pretty much guarantee that every mathematician in the world, that will be either at the top of the list or in their top 5. If your quest, this is the quest I charge you with as you go out into the world of mathematics, find me something cooler than that. Because, I mean, I know you're like, to prove that formula is true. Like, you see this thing right here? You see this thing right here, and you're like, meh. Do you remember what the general theme of that proof was? Do you remember what the general theme of that proof was? I wrote an inequality, right? A compound inequality. And then what did I do to that compound inequality? Do you remember? I had something, I had fn to the n plus 1 between m and negative m. What did I do at that point? Do you remember? I repeatedly did what? I wanted to get rid of the derivative, so what did I do? Integrate. I repeatedly integrated, right? The repeated integration is what results in this n plus 1 factorial. The other key to the proof was, if you have something to the nth degree, like Pn, the Taylor Polynomial of the nth degree, what happens when you take the n plus 1th derivative of anything that's to the nth degree? What's the third derivative of x cubed? What's the fourth derivative of x cubed? Sorry, what's the fourth derivative of x cubed? What's the third derivative of x squared?
0.
0. It always goes to 0. So what you need to know that proof. It's really, some of the mechanics in that proof are really important, but does the AP test you on proving that's true? No. Is it nice to know where it comes from? Yeah, it's actually not that bad. It takes a little while to stare at it and understand what's going on, but the idea is if you have an upper bound for the n+1th derivative, you can repeatedly integrate, and you get back, if you repeatedly integrate, you get back to the function itself. If you have the n+1 derivative and you integrate n+1 times, you're back at the function itself. You're back there. Do you remember the fundamental theorem of calculus? If you take the derivative and the integral again, where are you? You're back where you started. You're back where you started. So this right here is unfortunately something you do have to memorize right here. You do have to memorize this. And just about every, I think it's required that they ask you at least one multiple choice question about this. What's nice about it is, once you understand the general idea of what's going on, it's not that bad. It's really not that bad. It's really not that bad. What's the one key element of this that is the slight unknown? Like, you know what x is. A is what you're centering the Taylor polynomial around. N is the power of the Taylor polynomial. What's the one letter in there that all the mystery kind of revolves around? M. M is the one that it revolves around. Do you remember what M is? Does anybody remember anything about what M is? Element right here. This, but really to understand this, you have to understand what M is. M is an upper bound for this thing right here. You're going to get to do this a whole lot in mathematics. You get really used to doing things that are really clean. Like, you do a proof, and you have to do this, and this, and this, and this, and everything you do is 100% the same every time. When you're looking for an error bound, you're going to find a number that you know is greater than or equal to the n+1 derivative of the function. The only way to get your head around this is to actually do one of them. As Taylor polynomials get longer and longer, so as you add on terms, what do they become? As the Taylor polynomial itself, so the first degree Taylor polynomial, the second degree Taylor polynomial, they become more accurate, exactly, right. So the error bound, theoretically, should it get bigger or smaller as you get, it should get smaller. It should get smaller. Does that make sense, everybody? So when you're doing this, the error bound depends on what degree of the Taylor polynomial you're going to. So this formula, what do we have to know? We have to know the power n. You have to say like 4th degree power, exactly. Does that kind of make sense, everybody? And then we have to find this m, and then we put it all together. So let's do the same example you saw in the video. Let's just do one of them, okay? It's okay. Just quizzical face. It's okay. It's a lot of text. It's a ton of text. So this is the one I want us to do. Oh, where is it? It is right. Working with e to the x is kind of nice because it's the cleanest one. If I wanted the 4th degree Taylor polynomial approximation for this, can someone give me what this is approximately equal to when you're going to the 4th degree? Someone just read it to me. What is it? 1 plus what? X plus correct. And if I wanted to the 4th power, I'd have to keep on going. X to the 4th over. Now, is that exactly, are they exactly equal to each other? No, they're not exactly equal to each other, but we would really like to know how accurate it is. How accurate it is. How accurate it is. So let's look up here. How accurate this is. So this is another thing you have to understand from the notation. This is the error bound. This represents the error bound. And it's going to be equal to, f of x is the actual polynomial. That's the actual polynomial. But what's Pn x? What's that one? That's our approximation. The error is the difference between the actual and the approximation. And we're saying that this thing right here, the difference between the two, is going to be less than or equal to this thing. Blah. Right there. So let's just fill in the blanks. The error of this, meaning how far off this is at this point. Because what happens to the error bound as you go further in the Taylor polynomial? It gets smaller. It gets smaller, right? So we have m over, in this case, what's n going to be? No. Well, sorry, n is 4. Sorry, and what do we do to 4? Excuse me. Sorry about that. I was like, it is actually 4. n plus 1. Then we have, what is this centered around? So it gets to be x minus what? 0. And what power are we raising it to? To the 5. Okay, nice. So, what are we going to do? Here's this. Oh, I didn't clip it in. Sorry. Give a bound on the error when e to the x is approximated by its fourth degree polynomial about 0. About 0. Okay, this is not bad. So we can simplify this a little bit here. We have, what do we have here? M over what? 4 plus, so not 4, what is it, 5 factorial? Nice. Oops. X to the what? 5th. So we'd really like to find m at this point. We'd like to find m at this point. And m, you see this. n plus 1, you see this right here. You saw that. Do you remember that? Nice. So what we're trying to do here is, in this case, what is n? In our example, what is n? 4. So we have f5 like this. The 5th derivative. The 5th derivative. So how do we go about finding? Do you remember? I did this in the example. Do you remember how I went? It stays the same, right? It stays the same. This interval, when we need an interval when we're calculating error, because this right here, this polynomial right here, it's only going to be really accurate in a certain area. As it gets further out, what happens? It gets less accurate. That's why we need to keep on adding on terms. So in the problem, which I didn't paste in, we're looking at this interval from negative 0.5 to 0.5. So we're trying to figure out what's the biggest value the 5th derivative can be. We know what the 5th derivative is. What is it, Cameron? So we're looking for what's the biggest value when you're looking from negative 1/2 to positive 1/2. What's the biggest e to the x can be from negative 1/2 to positive 1/2? How do you figure that out? From here to here, you want the biggest possible value for e to the x. How do you figure out what that biggest possible value is? What type of function is e to the x? Can you use your hand to show me what it is? Is it always increasing or always decreasing? It's always increasing. So if you want the maximum value of e to the x, you have to go as far as you can to the right. What value is furthest to the right? 1/2. So what's the maximum value of this going to be? The max is going to be e to the what? E to the 1/2. This is where you get to do the really squishy math, okay? I know it's going to feel really weird. We're like, okay, the maximum value is e to the 1/2. What is e to the 1/2? That's what? Square root of e. You with me so far? So theoretically, do we now have our m value? Can we plug in our m? What is our m value going to be? Square root of e. So we could write it as the square root of e over 5 factorial times this. That's the maximum error bound. The maximum error bound right there. The maximum error bound. But what do we not really like having in there right there? We don't like having, well, we like a number, right? We'd like to know, like, let's read this here. It says, when e to the x is approximated by its fourth degree polynomial about 0 for x between negative 0.5 and 0.5. We plugged in 1/2 to find our maximum, the maximum of our derivative at the 5th derivative. So what do we have to plug in for x right here? 1/2. That's where the maximum is going to occur, so we need to plug that in. What I'm getting to is this. On the AP exam, are you going to see things written like this? No, you're not. You're not going to see things written like this. What do they like to write it as? They like to write it as decimals. So here's where you get to do some fun estimation. The square root of e, what is that approximately? Yeah, the square, if you do it on your calc, it's like 1.7 something, right? It's like, no, it's 2.7 square rooted, right? So what is it? 1.64, something about that, right? Here's the thing. On the AP exam, you get to actually do some estimation, which is kind of fun. So you know, for example, that the square root of e has to be less than, what's the next integer it has to be less than? 2. It has to be less than 2. If you're looking for a maximum error, you can just, what, all right, 5? 2. It's amazing. Well, that's also true, right? Yeah. That's also true. It's also true. So if you're going to do an estimate, you get to take this 2, and where do you get to put it? Replace it where what is? Square root of e is. So you end up with this thing right here. 2 over 5 factorial 1/2 to the 5th. Why? What's the point of doing that? What's the point? Why would we ever want to do that? Does this simplify nicely? Yeah, it does. So what do you end up with? You end up with 2 over 2 to the 5th times, what's 5 factorial? 120. Does that kind of make sense right there? So what do you end up with? 1 over 2 to the 4th times 120. Exactly. So you're going to do a lot of math in this field that looks like this. It's totally okay if you're uncomfortable with this at this point. Are you a little uncomfortable with this methodology at this point? A little uncomfortable? Let's try. Use theorem 10.1, which is what we were just looking at, to find a bound for the error in approximating the quantity with a third degree Taylor polynomial for the given function f of x about x equals 0. So let's do, and we're doing it for this value, e to the 0.1. So the first thing you can do, which is really helpful, is write out the what. What should I write out at this point? Let's write out the what? Let's write out the terms just so we can be comfortable with it. We're going to what degree? Third degree. So what's the third degree Taylor polynomial going to be? So what we're doing is we're comparing e to the 0.1 to when you plug in x is equal to 0.1 here. We're trying to find what's the maximum error. That's what we're doing. Do you understand what we're doing here at least? We're comparing this estimate to the actual value. Can anybody for a gold star tell me what that big nasty m over what is? M over what? n1 factorial to the... Is that right? What do we think? Ah, we're pretty good there. Nice. In this case, for this question, what are we centered around? I think it says we're centered around x equals 0, right? Is that kind of nice? So the first thing we know automatically right now is that this is equal to 0. A equals 0. Thank you. It's hard for me to talk and write at the same time for some reason today. In this case, what was n going to be? N is 3. N is 3, so they all turn into what? 4. So you have 4 factorial x to the what? 4th, right? Now, so in x is what? 0.1. So we're getting there. So this is going to be, it's going to go to m over 4 factorial. I know class is ending in a minute. 0.1 to the what power? 4th power. So this entire quest revolves around finding m. Now, what derivative do we need to look at right now? F4, right? We're looking at this thing right here. We're looking at this thing right here. And we're looking at it for 0.1. We're looking at it for 0.1. Do we actually know what this is actually going to be equal to for 0.1? Yeah, when you plug in 0.1 into the 4th derivative, what's our function again? E to the x. So what does this absolutely have to be less than or equal to? E to the what? E to the 0.1. Because can we actually take the derivative this time and plug it in? We absolutely can. We didn't need to find a maximum on this. We didn't need to use the entire stretch. So the maximum error is going to occur right there. We plug in 0.1 and we can get this. Okay, let's pause here for a second. Sorry, before I go here, I just want to point out one more shaded thing right here. When we're looking at the derivative of e to the x right here, when we're looking at the derivative of e to the x, why did we pick 1/2 right here? It keeps getting bigger, right? It keeps getting bigger. The maximum error is going to occur all the way to the right because that's going to be the biggest. So why do we plug in 0.1 right here? Because it's always getting bigger, so you pick the value farthest to the right. Yep.